Good afternoon, everyone. Today, I would like to explain about the distribution piping system. First, I would like to introduce myself. My name is Haikal Ramadhana Akmal, with student ID 2009, and my lecturer is Dr. Engineer Alcadria Asriputra. We jump to the topic. First one is the hydraulic design of piping system with the consideration. First is flow resistance with the available head and required head and pressure. And also the second one is the required flow rate, which is cost score, and also the sediment transport. In long pipe, resistant due to friction, surface dominant, and also equipment pressure loss. Next is about the distribution system design. First one is the loop network system. A loop distribution network has a flow pattern that change easily and are also irregular, making the hydraulic analysis more complex. There are two calculation methods commonly used. First one is approximation method. The loop network is simplified and also treated as a branch or tree system. The second one is the exact mathematical analysis using the Hardy-Cross interactive method to balance flow and also head loss in every loop. Before performing calculation, the estimate flow distribution for every pipeline segment must be assigned, including domestic and other demand components. Next is about the under real operation condition, like the pressure and flow rate differ across the network. In static or non-flow condition, the pressure throughout all the connected pipe equalize, and the line presenting this uniform pressure level is known as the hydraulic red line or HDL. During water flow, the hydraulic head gradually decreases along the direction of the flow. This loss of pressure head depend on the pipe length and also the flow rate and also the pipe diameter. The line representing this pressure drop is the hydrometric or hydraulic grade line or HGL. And the pressure loss per unit length of the pipe is expressed as a relative slope or slope, calculated as S equals to the pressure head divided by the length. Next is the objective of the water distribution. First one is to provide the uninterrupted water delivery. Second one is to maintain the pressure suitable for household and fire use. Next is for the minimize water loss through the leakage control. Next is the ensure uniform water quality across the network, and the last one is the support peak demand and emergency condition. The system aims to deliver adequate water quantity and quality across all surface area while ensuring operational reliability. Next is the key component of distribution network. A fully functioning distribution system consists of storage structure, pipelines, pumping station, and also control device, including the reservoir and also elevated storage tank, pump for pressure and flow regulation, transmission main and also distribution pipe, valve like gate, pressure reducing, and also air valves, and the last one is hydrant for fire protection and maintenance. Next is the design criteria overview. The design criteria ensure the system capacity and durability under the various hydraulic and also operational conditions. Include determination of demand categories, adequate pipe diameter selection, pressure and head loss evaluation, planning for future population growth, and also safety and redundancy in layout. Next is the water demand planning. Estimating water demand is essential for selecting pipe size, reservoir volume, and also pump capacities. Include average daily consumption and peak factor, domestic industrial institutional demand, the fire flow requirement during emergency, seasonal and climate relative variation, and the last one is allowances for future urban expansion. Next is the hydraulic analysis criteria. With hydraulic analysis evaluate how the water moves through the distribution system to ensure the network can deliver adequate pressure and flow under all operational conditions. This analysis consider flow velocity, head losses, pipe thickness, and pressure gradient, and also the network balancing. It ensures the water flow remains within safe and efficient velocity limit around the zero point 0.6 until 3 meters per second to prevent the sediment build-up and avoid pipe erosion. Calculates friction-based the head loss using Darcy-Weisbach and Hazen-Williams, accounting for pipe diameter, length, material, and also roughness. Includes minor head loss generated by fitting, band valve, and also the hydrants using the key value for R equivalence length. Next is the reservoir or water tower system. The reservoir and elevated water tower provide the gravitational pressure that stabilizes the distribution system. The structure stores treated water and releases it using natural hydraulic head, ensuring water availability during the peak consumption and emergencies, including use elevation or gravity to create natural pressure without continuous pumping, function as buffer storage to meet peak hourly demand and firefighting needs. Next is to maintain pressure during the pump failure and also the power outage, improving system reliability. Next is the help balance flow within the loop or bridge network by smoothing pressure fluctuation. Alright, next is about the advantage of gravity-based system. Gravity-driven distribution system offer significant operational and economic benefit due to their minimal dependence on mechanical equipment. They provide stable hydraulic pressure, excellent reliability, and also lower operational complexity, making them ideal for cities with the varied topography and high surface demand, including low energy consumption because the pump operate only for filling, not continuous distribution, and also ensure the consistent and stable pressure across the network, even during the demand fluctuation. And next is the reduced maintenance requirement. Since the fewer moving mechanical components are involved. And last one is the ancient firefighting capability by maintaining the reliable high pressure reserve. Next is about the distribution pattern overview. Distribution pattern define the physical arrangement of the pipeline within a surface area, the choice and of the layout effect reliability, cost redundancy, water quality, and also the system performance under the peak demand or emergency condition. Common pattern include the branch, tree, grid loop, and radial layout. Each pattern over the different level of redundancy and pressure stability influence ease of maintenance and ability to isolate fault section. And next is the effect water edge and potential for stagnation or contamination. Next is the branch or tree system. The branch system feature a straightforward pipeline layout where the water flow from the main line into the smaller branch while the cost effective and easy to construct. It has limited flexibility and lower reliability compared to local networks, include the water flow unidirectionally, simplify hydraulic analysis. Next, the lower installation cost due to minimal pipeline and fewer connection, and simple to design and also useful for rural or low density surface area. Next is the grid or lobet system. The lobet system interconnect pipeline in the closed network, allowing the water to flow from the multiple direction. This layout increases the reliability and high pressure distribution and also improve the water quality, making it ideal for urban and high density area. Next is the radial distribution system. The radial distribution pattern distribute water from the central reservoir or the pumping station into the subdivided zone. Each zone receives the water independently, allowing the better pressure control and efficient management for the local demand. Alright, this one is the case study in the Singapore water distribution. With the Singapore water system is recognized globally for its reliability, technological integration, and also sustainable management. The distribution network combined the advanced monitoring, diversified and the water resource, and also efficient pressure zoning to achieve the exceptionally low water losses. There is four major water source in this case, like the reservoir, imported water, desalination, and also the new water, which is the use smart, which is in this case the use smart sensor, SCADA system, and real-time pressure monitor. And next is the non-revenue water among the lowest in the world, like this 5%, and robust low network ensure the redundancy and pressuring stability. Alright, this one is the case study in Tokyo, Japan. With the Tokyo water distribution system showcase the engineering excellence with its advanced leakage control. seams resistant pipelines, and highly efficient district metering system. Its performance is a benchmark for a developed urban system. In this case, the leakage rate under 3%, among the lowest globally. The earthquake-resistant pipe designed to withstand extreme seismic activity, uses DMI district metered areas to monitor pressure and flow in the real time, and next the extensive use of the ductile iron and flexible joint. Alright, this one is the case study in the Netherlands. The Netherlands prioritized the water quality, innovative treatment process, and also the robust distribution system. The country operates the loop network with the advanced water quality monitoring, often without the chlorine residual, making strict control essential. Avoid this case is avoid the continuous chlorination like relies on ultra clean treated water. Then slow network reduce stagnation and contamination risk. Use continue microbiological and chemical sensor in pipelines, and also strong emphasis on pressure stability for maintain the purity. And this one is the conclusion of for distribution system. An effective drinking water distribution system requires the robust design criteria, appropriate the selection of the system type, and an optimized distribution layout. Learning from the leading global system strictness, local planning, and ensure reliable, suitable water supply for growing communities. And strong design criteria improve the pressure stability and the hydraulic efficiency. Next point is about the combination of gravity and pumping system enhance the reliability, and the loop network offer the best redundancy of the water quality performance, and the case study the highlight the importance of the advanced monitoring and alright, that's about the conclusion of our topic today, and thank you for your attention. I think I'm sorry for any mistake in my presentation. Okay, thank you for your attention. Assalamualaikum warahmatullahi wabarakatuh.